Okay, everybody, it is 12:02 on July 11th, 2025. Good afternoon. My name is Monica Driggers. I'm the Deputy Director for the Mass Rivers Alliance. Welcome to the Dam Busters 201 series. It's a collaboration between the Massachusetts Rivers Alliance, the Charles River Watershed Association, and the Mass Division of Ecological Restoration. This webinar series offers basic information about dam removal to managers from municipalities and nonprofits that may be considering such projects in the future. Please note that the series is not intended to advocate for the removal of any particular dam or dams. For the 201 series topics and exact schedule, please visit the Mass Rivers Alliance website at www.massriversalliance.org. We really and truly are still adding sessions to the series, so we do recommend that you check the site frequently for the latest information. You will also find all the information and recordings for last year's Dam Busters 101 series there. Today, Professor Noah Snyder of Boston College is with us for a presentation entitled Top 10 Ways to Tell If Your River Reach is Insensitive to Disturbance. This is a follow-up to Professor Snyder's very popular January 2025 presentation on New England dam removal research. Please mark your calendars for the next webinar, which will be on July 16th. So it will not be on the first Wednesday of that month, given the holiday in July. It will be about national issues in dam removal and will feature a speaker from American Rivers. A few housekeeping items. First of all, this session is scheduled to end at 1 p.m. Please put your questions in the Q&A function at the bottom of your screen, which Mass River staff is tracking, or hold them until the last half hour's question and answer session. Please put your name and affiliation in the chat. And lastly, these webinars are being recorded. Recordings and any other webinar materials will be made available on the Mass Rivers website. Lastly, we once again ask that you please complete the evaluation survey. The link will be posted in the chat. That survey really and truly has been crucial in helping us continue and expand this series and improve it. And now I'm delighted to introduce our speaker today, Professor Noah Snyder. He's a geomorphologist who studies the response of rivers to changes in land use, climate, and tectonics. He's a professor in and the chair of the Earth and Environmental Sciences Department at Boston College. He studied geology at Bates College, finishing in 1993. He received his PhD from MIT in 2001 and conducted postdoctoral research for the U.S. Geological Survey in Northern California. Since arriving at Boston College in 2004, his research has focused on rivers and associated land management issues in the eastern United States, such as dam construction and removal, reservoir sedimentation, and increased flooding associated with climate change. So with that, I hand it over to Professor Snyder.
All right. Hi, everybody. Thank you, Monica and Anna, for hosting this session today. I will go ahead and share my screen. All right, there we go. Yeah, so this is my return to the Dam Busters series. I'm delighted to be back. It's great. The level of participation, both just number of people who come to these and also the really stimulating questions that I had when I did this back in January, certainly made me want to come back because it's really fun to talk with all of you who are passionate about rivers like me. So this talk is top 10 ways to tell if your river reach is insensitive to disturbance. And I'll start with just a few acknowledgements. So this is work that I've kind of sort of ideas that I've been talking about over many years. And in particular, it sort of comes out of work projects that I've done with Matt Collins from NOAA Fisheries. And Matt and I co-advised Audrey Turcott, who was a master's student of mine at Boston College and is now working for the state of Colorado Water Resources. division. So, but it's also just kind of a compilation of ideas from many BC students and colleagues, probably many of you with whom I've had conversations next to and wading in New England rivers over years, and many other scientists and practitioners. And I've had funding from NOAA, the National Fish and Wildlife Foundation, NOAA Fish or National Science Foundation, Project Share, and Boston College for some of this work. So to get started, I'll just say, I will say like sort of a little fluvial geomorphology 101 here. And I like to think about rivers as there being sort of two end member types of rivers: imposed form channels, or what we might just call bedrock rivers, and self-form channels, which we would call alluvial rivers. And this is sort of, there's actually a lot of gradation between these two, but you might think of these as sort of end members. Imposed form channels, bedrock rivers, tend to be high up in the mountains. Self-form channels, alluvial rivers, tend to be in the lowlands. The key, probably most important way to think about this distinction is that imposed form channels have immobile bed and banks. So the actual geometry of the channel is controlled by, is not mobile by the river during any kind of normal flow. So it's typically exposed bedrock or very large boulders and things like that. That is in contrast to a self-formed channel, which, as the name self-formed indicates, the bed and banks are composed of sediment that was put there by the river. So, this is the beautiful thing about rivers, from a just what makes the study of rivers so rich, and how we can even think about rivers as almost like a living entity in some ways, is that self-formed rivers really make themselves. They construct themselves through the deposition and erosion that occurs on the inside and outside of bends, respectively. And so a classic self-formed river would maybe have a sand bed and silt and clay banks from overbank sedimentation during floods. In terms of events, we classically think of self-formed rivers as being formed by the bankful discharge, which corresponds to a recurrence interval, a flood with a recurrence interval around 2 years. These are rivers that have floodplains. That is, and the height of the floodplain is actually something the river has, some ability to adjust over time. Whereas imposed form channels have are the morphology, the geometry of the channel is set by very rare large floods that are capable of eroding bedrock or moving the very coarse materials delivered by landslides, for instance, like boulders in the bed of the channel. In terms of the delivery of sediment downstream, if we think about bedload transport, the rolling or tumbling or movement of gravel or sand along the bed of the river is what sort of classically sets the morphology of a river. And the rate of that in a bedrock river is set by the availability of sediment coming in from the watershed upstream. And classically, that means what we call that is supply limited, meaning the amount of sediment delivered downstream is a function of the supply coming off the hillsides. Whereas in a self-formed river, the bed load is set by the capacity and competence of the channel, which corresponds to the slope and the width and the depth of the channel at bank full classically. And so the amount of sediment, bed load sediment, that moves downstream is a function of floods and transport events. There's plenty of supply of sediment because the bed and the banks are potentially available sediment for the river to move. But there's less, but there's not enough energy necessarily, not enough energy to transport all that sediment, which is why the bed is actually composed of sediment that the river can potentially move. Okay, so these are the two end members that we like to think about. And in terms of restoration, you're going to have a lot more ability to change a river valley or a river bed if it's self-formed, because it's composed of transportable sediment as opposed to a more imposed form bedrock river. All right, so a lot of this work comes from work on or thinking that a lot of this thinking comes from work on salmon habitat and restoration of salmon habitat, or in general, restoration of habitat for migratory fish species, such as herring and shad and things like that. And certainly, this series is really focused on dam removal. And my talk in January was focused on dam removal. This talk is really more relevant to restoration, of which dam removal is a form of stream restoration for sure. But we're really talking about restoration of fish habitat and restoration of natural processes in rivers. And a lot of this kind of thinking about restoration of fish habitat comes from work in the salmon rivers of the Pacific Northwest, or Alaska, as we see on the right there. And it gets to this idea that, as I said before, rivers have inputs, which are water, fine sediment, coarse sediment, and large wood, all enter rivers from the watershed. And then processes like floodplain inundation, sediment transport, and bank erosion move those materials, water, sediment, wood, downstream. And that the interactions of those materials with those via those processes give us the morphology, the form of the floodplain, the height of the floodplain and what it's composed of, and the channel, the bars, the pools, the riffles in the channel. And for fish, those are the habitats that where they live. They live in floodplain and riparian channels. They live in, and then for salmon, there's spawning and rearing habitat needs that are slightly different in different channels. And so, you get this sort of idea of sort of materials coming into the watershed, coming from the watershed into the channels, that leading to the morphology of the channels, which gives you habitat, which, to some extent dictates the abundance of fish species, because it's commonly thought that certain fish species are limited by the availability of habitat. And of course, that's one of the big reasons that we do dam removal, because dam removal is a quick way to open up stream habitat to migratory fish like salmon. So classically, we think about, and I'm talking to you from Boston. I think mostly this is a New England oriented group, and certainly the northeastern United States and maybe adjacent Canadian provinces as well. And so primarily we're interested in Atlantic salmon, and we certainly think of the freshwater habitat needs of Atlantic salmon focusing on wood in the channel and adjacent to it, both trees to provide shade and cover, but also wood in the channel to provide literally places for small fish to hide and rear. We also need mobile gravel beds so that the fish can actually construct the nests called redds in the bed of the river, on the bed of the river. So that's sort of like the classic habitat needs of salmon. And, salmon are Atlantic salmon are a critically endangered species here in the New England states in the United States. And so there's a lot of concern and desire to restore salmon habitat around New England, especially in Maine these days. And so some of my research has been involved, actually over the last 20 years, I've had various students working on various aspects of salmon river morphology and its relationship with dam removal and stream restoration more generally in New England. And so this is one of my students, Audrey Turcott, who I mentioned earlier, flying a drone over the Narragansett River in Maine. And next to her is a large tree that was actually intentionally dropped into the channel, pulled into the channel to restore large wood to the channel, to create that complex mosaic of habitats that are thought to be really important for salmon and for other migratory fish. And so this project that Audrey worked on was really focused on trying to evaluate whether these large wood additions, restoration of large wood to the channel, was actually having a geomorphic effect. Was it creating habitat by causing scour of pools, adding complexity of bed substrate size across the channel, adding complexity of velocity across the channel, provide, things like that. Was it having the desired habitat effects that motivated the restoration? And these projects get done in a couple different ways. Sometimes trees are pulled with their root wads from the sides of the channel. Other times, more structures are built out of logs and posts in the bottom of the channel, again, to kind of create stable wood that then can, during floods, hopefully allow the river to start to erode around them and create some scour pools, deeper pools, and some variability in the morphology, which, as anybody who fishes knows, fish like diversity, three-dimensional variability in the channel. Well, to cut to the chase, this talk isn't really about Audrey's work. What we found was that in terms of the effectiveness of adding wood to channels, which really is the goal is generally to promote ecological and geomorphic complexity within channels. We studied streams at several sites around the New England states and found that only about a third of the study sites had the expected results in terms of increased variability in depth or velocity in the channel as a result or connected with these wood additions. So in other words, most of the streams were not changing. The morphology was not being heavily influenced by the wood. And this kind of gets to this concept that a lot of people in ecology and stream morphology are thinking about now, which is sensitivity to disturbance. So, you might think of disturbance as a bad thing, but it's a lot of times to recreate the natural processes in a river, we like to restore kind of the natural set of processes that we know exist in channels. And one of those processes is wood falling into the channels and that driving scour and deflection of the channel, and that then creating ideally habitat or complexity in habitat. And so, and another form of disturbance on some level is construction of a dam. And so removal of a dam is a way to restore continuity of sediment transport in channels and make them then more, ideally more complex systems in terms of the habitat. The thing is that these ideas of stream restoration around, for instance, large wood additions and things like that, and really a lot of our knowledge of the connection between the sort of restoration ecology of salmon comes from streams in the Pacific Northwest and Alaska, which are much steeper rivers in a much more tectonically active landscape than we have here in New England. And as a result, there's a much greater sensitivity. I would argue there's a much greater sensitivity to disturbance. So for instance, a huge disturbance here is the clear cut of this volcanic mountainside in Washington. And you can see here, that the clear cut is clearly associated with the scouring out of these debris flow channels, which then leads to delivery of a lot of sediment to the river. You can see that the river has this reddish color, probably from suspended load coming off this soil erosion, as well as a lot of deposition of bed load from gravel coming off the hillside. So a strong sensitivity to disturbance. And so if you want your restoration effort to, if you're doing a restoration project like adding wood to a channel, you want to know whether the channel is going to be sensitive to that disturbance, that addition of wood, for instance, to the channel. And so this led me to this kind of quick and easy ways to diagnose whether your stream is sensitive to disturbance, or as I like to phrase it here, insensitive to disturbance. And as a child of the 80s, of course, I love top 10 lists because I love David Letterman. And so I framed this as a top 10 list. I realize that analogy probably doesn't work for many of you, but those of you who watched David Letterman at 12:30 at night in the 80s will remember the top 10 lists. I think he went on to the 90s too and all that. Anyway, so what we're really, if we're talking about whether streams are going to be insensitive to disturbance and whether they're going to be, therefore, if we do a restoration effort, it's unlikely to cause change in the channel. What we're looking for is evidence for imposed form channels as opposed to self-formed or alluvial channels, low sediment supply, so not a lot of sediment moving through. Sediment is ultimately the tools with which rivers can build their morphology. And we're also looking for evidence of rare bedload transport, a non-deformable bed. And we're going to start at large spatial scales in our top 10 list and long time scales and go to smaller spatial scales and short time scales. And I'm actually going to have 12 ways by the end of this. So it's not top 10, it's top 12. All right, so I keep having to hide the meeting controls so I can see the top. Anyway. So the first kind of largest, most macro scale is I'm showing you a map of the world. And what I would say is that sensitivity to disturbance is very much connected with sediment load and erosion and and erosion rate. And the first order control on erosion rate in a watershed is how fast that watershed is uplifting due to tectonic activity. And so the Ring of Fire around the Pacific, of course, has these places where the Pacific plate is converging with the Eurasian plate or the North American plate, and this leads to volcanoes and mountain ranges and basically the uplift of rocks relative to sea level. And that leads to steeper mountains and much greater erosion rates and therefore much greater availability of sediment in the channels. And so on the left, we just sort of see earthquakes around the world. And on the right, we see work by Milliman and Farnsworth that just estimates sediment flux out of major watersheds around the world. And so what we notice is that our region here on the passive margin of the North American plate and the Atlantic coast of the North American plate has very few major earthquakes, relatively speaking. And it has a very low, the yellow color here is the lowest suspended sediment flux to the ocean. So this part of the world is tectonically inactive and has low erosion rates, which means that there's not a lot of sediment available coming from the watersheds into the channels and available for the rivers to move. The next way is the next sign of insensitivity to disturbance is recent continental glaciation. We are in a part of the world here in New England that was under a mile or more of the Laurentide ice sheet about 20,000 years ago. And so that is a major disturbance, absolutely. And I would argue that compared to that, human impacts on New England rivers, possibly aside from dam construction, but other human impacts on New England rivers are relatively small compared to the dramatic impact of glaciation. And I would argue, and a lot of my work argues, that New England rivers are really still very much in slowly responding to this legacy of glaciation. The rivers of our region flow across a landscape conditioned by continental glaciation. That means that where sediment is available is a very localized thing. Much of the uplands of New England are, as all of you know from walking around this landscape, is much of the uplands have very thin soils. That's because the soils were stripped away by repeated glaciations over the last 3 million years and deposited in places like Cape Cod and Long Island. There are thick piles of sediment scattered around locally around the New England landscape. For instance, places where there's deltas associated with glacial lakes, like we see here, and valley bottom glacial till deposits in some cases, as we see on the bottom slide here, both of which are from the South River watershed in western Massachusetts. And where these exist, these are really important sediment supplies that create more alluvial channels downstream of those sediment sources. But much of New England has very thin soils and very low sediment supply. So another indicator of insensitivity to disturbance is just river reaches that are downstream from main stem lakes or wetlands. So this is a picture of this is the Sheepscot River in Maine here, and you can see this lake called James Pond next to the river. But what you can also see is this large wetland complex here that, if we outline it, is something like this, just in sketch outline. And what I interpret this actually as is the filled version of a much larger lake basin that, the river has filled it in and turned it into a wetland. And it's filled it in because upstream there are, I'm going the wrong direction here. Upstream there are glacial deposits that the river can erode and then fill in that lake basin. But then downstream, there's very low supply available because all the sediment is dropping out in this lake basin. Lakes are geologically ephemeral features. Now, as a geologist, we think in long time scales, which for me as a geomorphologist means, I think in, tens of thousands of years. Lots of my colleagues think in millions and billions of years. But over any kind of geologic time scale, lakes are ephemeral. Lakes are a temporary feature in the landscape. And in fact, where we have lakes in natural lakes is pretty good to first order. Where there are natural lakes are where there used to be continental ice sheets. That's not completely true, but most natural lakes, certainly in North America, are where the ice sheet used to be, because glaciers are great at scouring out basins that then fill with water during interglacial times and create lake basins that slowly infill as rivers deliver sediment to them. So upstream here, there's thick glacial deposits, thick piles of sediment deposited by the glacier that the river has cut down into. This is the Sheepscot River cutting into one of these glacial deposits. And that process has led to the partially infilling of this lake basin, which sort of turns a lake into a wetland with a river flowing through it slowly. All right, so now bringing it down to something, to dams, a really good indicator of insensitivity to disturbance are reservoirs upstream of dams that have little obvious sedimentation in them. And this is the Cooper's Mills Reservoir, the former Cooper's Mills Reservoir. That dam's been removed. And it makes dam removal in many cases, much simpler if there's little sedimentation in the dam or in the reservoir, because you don't have to worry about managing all that sediment. Although I would argue that in our rivers, that sediment is probably beneficial from a habitat standpoint, unless it's contaminated, of course. So many New England rivers have dams with reservoirs upstream that show very little evidence of sedimentation, as opposed to large reservoirs in the Pacific Northwest where there's spectacular sedimentation occurring over the decades. And that's something I've studied a lot around in different parts of the country. But in the main, in New England, our reservoirs don't have much sediment in them. As opposed to, this is a picture of, I love this picture. This is the Conway Electric Dam on the South River in Western Massachusetts. And I think it's a 40-foot high dam or something like that. You're seeing the rim of the dam here and people standing on the sediment deposited in the reservoir. So it's full to the rim, literally, with sediment. And you can see that those people are here in this air photo, and you can see the river flowing through the reservoir, but the reservoir is just completely full of sediment here, the former reservoir of the Conway Electric Dam. Note that there's the top photo and the bottom. The top photo is oriented the other way, the opposite way as the bottom photo. In other words, east is to the left in the top photo, and it's to the right in the bottom photo. But in any case, some dams in New England have lots of obvious sedimentation, but that's not, I would argue, the norm. And most dams have very little sedimentation behind them. This one does because there's a lot of glacial deposits in this watershed that the river can move and fill in low energy environments like reservoirs. So zeroing in a little bit more, I like to think a lot about longitudinal profiles, which is a graph essentially of distance along the channel in the y-axis and elevation of the riverbed or the water surface on the x-axis, on the y-axis, and distance on the x-axis. And so this is the west branch of the Sheepscot River in Maine, and longitudinal profile. And you see that it has these characteristic flat sections, which are probably these filled wetlands, very low gradient sections, and then steep sections that are much higher gradient. And in particular, where we have these convexities, where the profile goes from flat downstream to steep, that's where we're going to have a lot of insensitivity to disturbance, because the flat section has low energy and sediment can't move through it. So it deposits in these flat sections. And then you get to the steep section and there's a lot of energy in the channel, but there's no sediment to move. So it's a very sediment starved environment, as opposed to, here's a couple of these convexities, as opposed to the concavities downstream where the river has a decreasing slope, that's going to be corresponding to places where you're going to get deposition in the channel, and you might have a more alluvial condition. Relatedly, low gradient longitudinal profiles, less than about, say, 0.5% or 0.2%, are places that are just going to have very low bedload transport, which is going to mean very low sediment supply and a lot of insensitivity to disturbance. So like there's in many New England rivers, there's long stretches of very low gradient channels, often with adjacent wetlands next to the river. Perhaps the most classic way to tell if a stream is alluvial or not is, does it have the classic features of an alluvial channel, like meanders and point bars and cut banks? Here's a LiDAR image of a part of the Narraguagus watershed in Maine, where you can actually see these features are glacial deposits in the river valley. And the river is basically flowing between these glacial deposits, but it is not, we don't see a lot of evidence for it migrating around. As opposed to, so here's another picture of that sort of same area of the Narraguagus. Farther downstream, the Narraguagus has lots of meanders where there's clear evidence that it's migrating around over decadal scales. And that the channel, there's paleo channels and oxbows and cutoffs and what are called scroll bars and these classic alluvial features. And this is evidence of river migration and evidence of the river being self-formed, of the river flowing through sediment that it deposited, and therefore during floods, it can erode and move. Just some pictures of the lower Narraguagus. The upper Narraguagus, where a lot of these wood additions were done, is very insensitive to disturbance. The downstream part, this is in the coastal down East Maine, where I've done a lot of research. The downstream part, there's a lot of evidence for these alluvial features like meander migration and things like that. So, of course, another really good indicator of insensitivity to disturbance is bedrock channels. And we see these throughout. It's a classic characteristic of New England rivers is you have these little bedrock or big bedrock waterfalls. And, often we put bridges there, and we put bridges there because the channel is very insensitive to erosion. Erosion of bedrock is a very slow process compared to erosion of sand. And so we often put bridges at places where there's bedrock in the channel, but these are places where by definition, the river is eroding very slowly. And in fact, bedrock in the channel is evidence of a lack of bedload supply. If you have a lot of bedload coming in, that will carpet the bed with sand or gravel. But if you don't have a lot coming in from upstream, then the river becomes sediment starved and you have a bedrock bed. You can do whatever you want to this river. It's not going to change the morphology because the bedrock erodes so slowly. It only erodes during very rare, 100-year type floods. And even that is a slow process. So it's a much less dynamic system than, even though it's got a lot of white water and, looks very vigorous, but it's very geomorphically dead, very geomorphically slowly changing. Another really good indicator of lack of insensitive disturbance is a lack of unvegetated bars. So a lot of New England rivers look like this, where you see bedrock or you see boulders sticking up out of the channel that probably almost never move, that were probably put there by glaciers and have just been sitting there for, more or less there for 15,000 years. And the banks and the edges of the channel are filled with riparian vegetation with woody stems and things like that, as opposed to a more alluvial channel where you have bars, in the bed adjacent to the channel or on the sides of the channel, you have point bars composed of sand or gravel that are unvegetated, and that by definition that or if they're unvegetated, that is evidence that they're moving fairly frequently, and so rooted vegetation can't take hold. And so evidence of, really great basic evidence of an insensitive channel is a lack of these kind of unvegetated sand or gravel bars. Another similar thing is in-channel rooted submerged aquatic vegetation. So this again is the Narraguagus River. You have lots of this rooted, aquatic vegetation in the channel. This is strong evidence that the riverbed is very immobile here, because if it were more mobile, you wouldn't have vegetation holding on, growing seasonally in one place on the riverbed. Also, little cross-sectional variation in depth. So, like a channel that's got a very sort of flat cross section, as opposed to having a lot of variability. In terms of deeper pools and shallower riffles across the channel, or shallower bars across the channel. We found certainly on the Narraguagus River, where a lot of this work was done, that there's that the channel, whether or not there's wood in the channel, there's not a lot of evidence of variability in depth. And then perhaps the simplest way to tell if your river is insensitive to disturbance is, what does the bed look like? A lot of New England riverbeds have boulders or cobbles on the bed that are dark and algae covered and biofilm covered and look like they don't move. And in fact, when you try and wade on them, you slip around because there's so much moss and algae on the bed, on these boulders or cobbles on the bed of the river, that that's great evidence that they're never moving, or very, very rarely moving. And if they're not moving, then the river is not going to be sensitive to disturbance. If you try and, if you're trying to change the morphology of the river, it's going to be difficult to do, because the bed is composed of sediment that the river can't move under normal circumstance. So here's a summary of my top 12 ways to tell if your river reach is insensitive to disturbance. And again, if you're looking to do a restoration activity that's, with a goal toward creating complexity in habitat, like adding wood to a channel, you are probably going to need to find parts of the river, channels where the river is likely to be sensitive to that disturbance. And that primarily means is moving bed load on a regular basis. So that's my top 12 ways. I appreciate your attention, and hopefully we can have a series of questions now about what I've had to say about kind of, again, a perspective on rivers here in the northeastern United States.
Wow. Thanks so much, Professor Snyder, for another presentation, absolutely chock full of information that I think will probably be incredibly useful to our audience. We have a couple of questions in the Q&A. So the first one is, what does insensitivity to disturbances indicate for restoration? Would an insensitive river respond more or less ideally? I'm a little confused by this and new to river restoration.
Well, so again, it's a great question, right? So if the purpose of your restoration activity is to elicit a geomorphic response at the local level, so there's certainly a lot of, fish-like complexity, local complexity in habitat. That is quite clear from, the biology of migratory fish. They like there to be variations in the depth across the channel, in the size of the substrate, in the temperature, in the velocity, due to, literally have pieces of wood in the channel. All those types of things are thought to be good for fish. If you're doing a restoration activity that's trying to build complexity in the channel, then you want a channel that is going to be sensitive to that disturbance, to that restoration activity, like adding wood to the channel. So if that's your goal, you want sensitivity to disturbance, which means you want an alluvial river, a river with a bed that is frequently mobilized, because that means that the river is going to adjust and change as a result of the restoration activity. Now, on the other hand, very often, from the standpoint of permitting a restoration activity like a dam removal, insensitivity is probably a good thing, because you're not going to change the river downstream very much at all. If there's no sediment stored, or very little sediment stored in the reservoir, if you take the dam down, it doesn't change the river downstream very much at all, because you're not adding a slug of decades of sediment that has been building up in this channel, in the reservoir. And certainly, like the removals of dams on the Penobscot and Kennebec rivers in Maine, those are some of the largest dam removals that have been done in New England. Those require no management of sediment whatsoever, because there was no sediment stored in the reservoirs, because it was all trapped way farther upstream in other lakes and reservoirs elsewhere. So, again, this talk was very much focused on practitioners that are really interested in restoration of salmon habitat. But if you're just restoring continuity of water and sediment flow, and therefore migratory fish, by doing dam removals, then insensitivity may be actually a plus, because you're not going to have a big response outside of your project area as a result of your activity. Does that make sense? So it's a little bit of a different type of restoration that we're talking about here than dam removal.
Fantastic, thank you. The next question is from Dan. You called the Bedrock River channel, quote, dead, as you were discussing channel bed variation over time. That is clearly the case with the rock we have in New England, but how does that factor into the analyses with soft sandstones or other more easily erodible bedrock beds?
Yeah, so I probably shouldn't have used the term dead. I meant geomorphically dead, so just not very dynamic in terms of, like beautiful meandering rivers that are like migrating across their floodplains over decadal scales and things like that. Bedrock rivers, again, by definition, if the bed is bedrock, that means that there is not very much bed load coming in. There's not sanding, there's no supply. The supply of sand and gravel coming in from upstream is much less than the ability of the river to move it. So it's all being moved away, and you're only left with what the river can't move, and that's the bedrock. Certainly, New England has famously very hard crystalline bedrock. We're kind of mid-crustal metamorphic rocks here. And softer rock erodes faster, for sure, and will create different types of sediment. And so absolutely, and there's a whole lot of research, and it's actually an incredibly difficult problem to tease out the role of the lithology, of the hardness of the rock in any kind of quantitative way, in how that affects bedrock morphology. And so, river morphology, how bedrock strength affects river morphology. And I'm clearly sort of gearing this talk to New England, where basically all the rock is super hard. And softer bedrock definitely is a little bit of a different, can be a little bit of a different story in terms of how the river responds to disturbance and things like that.
Thank you. We've got a few more questions. I'm going to note the time. We can go over by a little bit if necessary, and/or we can ask Professor Snyder to answer questions, and we'll get back to everybody by email. But the next question is, do you perform this analysis for specific river sites? If not, who can and does that kind of analysis? And actually, I'm going to add on to that because I noticed that you had the longitudinal profiles of rivers. I'm just wondering if people who are new to river restoration and dam removal can find those kinds of longitudinal profiles at a particular source.
Yeah, that is okay. So some really great questions there. So starting with kind of the idea here is, and someday I'll get around to writing this paper. The idea with this talk is to provide practitioners, people who aren't necessarily fluvial geomorphologists, but people who are, working for nonprofits or working for consulting companies that are interested in doing restoration activities with an eye toward building habitat complexity. Ways to sort of diagnose whether a river is likely a good candidate for restoration activities, or what's likely to happen if you do a restoration activity. And so my thought is that, all of you, and you're out there in your waders in a river, you can kind of get a sense of like, oh, here, look, I'm looking at the bed of the river and it's all covered with mossy boulders. And it just doesn't, if I think about it, yeah, this doesn't seem like it's moving ever. Whereas, oh, I'm in this channel and there's, the bed of the river is composed of clean sandbars, that are like moving visibly as I'm standing here. Like that's a much more sensitive system than the moss covered boulders of many New England rivers or bedrock rivers. And so it's just like a way of sort of diagnosing whether your river is, that idea is like sort of simple qualitative ways to tell whether your river is kind of more alluvial and therefore likely to change dynamically, or more bedrock, imposed form, insensitive to disturbance, unlikely to change in any kind of dynamic way. Now, I love longitudinal profiles, and I wish there was, I think there are GIS-based tools for pulling longitudinal profiles, but it definitely requires a little bit of training, but there's a number of them. I think there's one called Topo Toolbox. There's something, R tools. I don't know all the different tool packages because I kind of do it. I have my own methods that I use, but there are definitely like add-ons to GIS packages that will allow you to go from a digital elevation model to a longitudinal profile. And they are really a useful way of diagnosing kind of where in the watershed you are. And I think a really underappreciated tool, but again, they're not as readily available as I think would be nice. But if you're interested in that, I can, email me and I can point you in the direction of some of the different tools that are out there.
Thank you. I mean, I think just knowing that they might be available could be helpful to people who are planning projects. Okay, we've got 2 questions and just a few minutes left. So if your intention is to increase, this is from David, if your intention is to increase flood holding capacity of a river, especially upstream of a dam to be removed, how would you view this in terms of sensitivity to the sensitivity disturbance paradigm?
That's a good question. I guess I would say that insensitive channels are probably in the main have less spectacular, aren't eroding much during floods and things like that, so are more stable during floods. And so it may be, again, like insensitivity to disturbance may be a desirable characteristic of a channel if you're doing something like a dam removal. Whereas, a more sensitive alluvial river, if you change the system, it's going to erode and move around, and it's going to respond much more directly, and that might have negative impacts on infrastructure in your river valley due to erosion or flood risk. But I think probably I'd hesitate to make too much in the way of generalizations there, because again, primarily what I'm trying to give people is a way, just another lens through which, when you're looking at a river reach, a section of river, like what's going on here? How dynamic is this? And I think that in the main, a lot of New England rivers are very not dynamic. They're not moving around. They're not very alluvial. And therefore they're not very sensitive to disturbance, which again, can be a good thing from a restoration standpoint, or it can be a bad thing if you're trying to build habitat complexity.
Okay, and we're starting to close in on time. I'll take the last question, but I will also remind everybody to complete the evaluation survey in case you have to drop off. The link is there in the chat, and we'll also send it out again. Again, it's super helpful to us. Last question is from Jeff. If there is insensitivity to disturbance, then it would seem like more mechanical/constructed restoration solutions would stay in place. This is in contrast to doing restoration actions in rivers that are sensitive to disturbance, where you could build a log jam in 1 year, and then a few years, the river could migrate away from your restoration action/dollars. In cases like this, it makes more sense. It makes sense to restore processes instead of building missing habitat features. Do you see this practice in the New England region, or in the Northeast? Sorry.
Yeah, so for sure, that there's a lot there. So for sure, if the river is really sensitive and has a mobile bed, it's going to be hard to make a stable, wood structure. On the other hand, if the river is really stable, the channel, without eroding at all, can move a huge amount of water down it, which also might make wood structures kind of hard to keep in place. I totally agree with the restoration of process paradigm. Like, that's what we want to do. And that's why dam removal is such a great thing, right? Because what dam removal does is it restores continuity of river processes. And especially, I really like to think about bedload sediment, sand and gravel, typically in rivers, as the tools that the river has to respond to changes. And dams block bedload transport, and in the main, not completely, but certainly they impede bedload transport. So we take dams out, it restores that continuity, that sort of mobile carpet of bedload that rivers are ideally supposed to have, although often they don't because of glacial legacy and things like that. And so dam removal is sort of, to me, an ultimate kind of process-based restoration. But again, I think, I don't know, adding wood back into channels is definitely kind of a do no harm, at least from a standpoint of like making habitat complexity. But I think you have a lot less effect if the river is insensitive to disturbance. And often adding wood back to the channels, even if they're not stable, that wood will wind up, somewhere, and through some process of wood transport will wind up somewhere, and will probably, eventually probably stabilize somewhere. And maybe that's okay, even if your project blows out. So it's a mixed bag, I guess I would say. But I think that I think that some of the activities in these really insensitive post-glacial rivers in Maine, I think that you could argue that there's not a lot of bang happening for your restoration buck if you're putting in wood and it's not causing scour of the bed and not causing increasing complexity aside from the wood itself. You want to restore process. You want to restore bedload transport as a process.
Thank you so much we're at time. I know there's one more question which we will get answered via email, Lisa, don't worry about it. I want to thank you again, Professor Snyder, for your second fantastic presentation for us. I mean, I'm sure everybody on the webinar learned a great deal. I know last time you did a talk, I got like one email after another saying how much everybody enjoyed the presentation. I'm sure I will get that once again. Just a reminder to all once more to please fill out the evaluation. We will see everybody on July 16th for national issues in dam removal with American Rivers. And everybody, we hope you really enjoy the summer. Maybe it'll stop raining on the weekends. Thanks so much to everybody. Bye-bye.
Thank you all.